Okay, hello everyone. This is the lecture for February the 13th. So this is for the February 13th lecture. This is not, well, we already passed the midterm, hopefully. I'm recording this before the midterm. So how to link this lecture to the previous lecture? So we've talked about directions, we've talked about distances, we've talked about levels. We've talked about angles. So the objective of this lecture is to talk about another instrument called the total station. I'm going to go through the different components, as you see here, of the total station. It's basically going to measure angles for us, both vertical and horizontal angles. And I'm going to show you the idea about measuring angles, how we measured angles in the, well, I wouldn't say history or the early days. We are still using these equipment somehow now. And then measuring distances here with an equipment called EDM, electronic measuring distance. And then how we integrated these two into our new system, into our total station. So that's the objective of today's lecture. And then we'll see some kinds of these total stations. We'll see some applications. So this is the objective of this lecture, February the 13th. Okay, so what is a total station? A total station could be defined as merging two of our old equipment. Again, old here is a little bit, I wouldn't say incorrect, but we still use some of these equipment somehow. So in the early days, we had what we call a transit. We had what we call a transit to measure angles, whether these angles are vertical angles or horizontal angles. And again, I would like to make sure we still remember that in surveying, we measure two types of angles here. If you remember, let me grab this here, this nice tool. This is our horizontal plane. This is our vertical plane. And then in surveying, if we can measure horizontal and vertical angles. Horizontal angles measured in a horizontal plane. So what we do, if you remember, we have our equipment, we level our equipment. By leveling our equipment, this surface becomes a horizontal surface, so we measure angles in this surface, which are horizontal angles. And angles perpendicular to this surface are going to be vertical angles. Okay, so back here, hopefully this just do a quick intro. So back here, this is the transit. I'll show you some of these nice transits. And then plus this, so remember, we are talking, the objective is we are talking about total stations here. So plus the total stations or plus the angles, we also are going to measure distances. We are going to measure distances between the center of the instrument and the reflector. And I'm going to show you that. So if you merge these two into an equipment, that's a total station. That's what we call a total station. And then we add a microprocessor, we add an electronic storage unit, like just a memory card or something like that. That becomes our total station. The purpose of the microprocessor or the chip here, the computer chip, is to do the calculations for us. So the equipment is going to measure angles and it's going to measure distances, but then the microprocessor can compute components like vertical distance, horizontal distance, coordinates from what you measured. Okay, let's see what a transit is first. So this is an image here of a transit used in the very early days. I have to be honest here, I haven't used transits for sure. I mean, these were used in the early 90s. But this is a scheme diagram here for a transit. Well, actually, this is a picture of the transit. The other light, I got you a scheme diagram. And this is the actual transit in the box here. Now, transits did have different tripods here. We use them sometimes in surveying competitions. We teach the students how to set them up, and sometimes we got some teams to measure angles with transits. But I mean, they have been abolished long time ago. Usually what you see in the transit here, if you looked at it, there is the scope here, and then you see this. This is what we call, let me point it out because I'm not sure if you guys will be able to see the mouse here. This here, and I'm going to highlight it here. Let me make sure it gets to the red. And then this thing here, I'm going to point to it. This is what we call here. Let me get this to paint better so I can point it better, and then I can share paint. Okay, so this thing here, this is here what we call the vertical circle. You see, this is the vertical circle. It's like a protractor here. If you look at it, it's like a protractor. We'll see some image. And that, once this equipment is set on the tripod, is what we use to measure the vertical angles. If you have it on a tripod like this, tripods of these ones were a little different than ones we have now. And then the other part that is this part that I'm highlighting here. Maybe I made it worse, but this here is what we call the horizontal circle. And it's also another protractor. So this is here the vertical. Let me make this a little bigger here. Vertical circle. And this is here what we call the horizontal circle. So these here are what we use to measure both vertical and horizontal angles. And you see the vials here, this vial, and let me clear the arrows here. This vial and this vial. These are two perpendicular vials that we use to level the equipment through the screws. So it's kind of what we have now. It's just a little bit different in setting it up. These are the screws we use to level, and these are the two level vials. So it doesn't really have a circular bubble here. This is the old transit here. This is the very old transit. And this here is where we set the plumb up. Of course, we didn't have laser plumbing at that time. Okay, so going back to the total station. So that's the transit here. And then after the transit, if you look at the transits here, to read the transits, you have to look externally here. So then they came with what they call the theodolite. That's the scheme diagram of the theodolite. That's an actual theodolite here. So the big difference between the theodolite and the transit here is they have now the horizontal and vertical circles inside these compartments here. So this is what we call open versus closed design. I highlighted these differences here, the difference between a transit and a theodolite. So you really, I'm going to go over this, read them quickly, but you really will find everything in this slide here. Okay, let me go to paint and put both of them together. So this is a transit here. This is what we call the closed design here. This is the vertical circle, and this is the horizontal circle. Now we see our screws that we use. These are the screws that we use here. Now, how do we read the vertical and horizontal readings here? Well, the horizontal reading and the vertical readings are going to be somehow through some mirrors here projected, and we can see it, maybe this is the wrong arrow here, we can see it through this lens here. So this lens is where we can, this one here is where is the A? This is where we can look inside and see our readings. So now, since they are closed, we can't really look outside. We can look through this lens and see the readings. And if you see this part here, I used theodolites a lot. I didn't really use transits, maybe in a competition or something. This is here. You see this piece here. This piece here, if you open this part, you will get the light inside, and the light will lighten the whole thing from inside, so you can see it. And in daytime, you reflect the sun light inside, or in nighttime, you can use any outsource light. Okay, we see also some of these knobs here. This is one knob. This is another knob. These knobs here are either used to close the circles or to prevent the circles from moving, so you can't really force it to move, so it makes the precise measurements. And then once you are done with the measurement, you can release the knobs and then turn it around. And there are a couple of knobs here. You see the circular bubble, and on the other side here you see the level vial here. What else? This is what this lower piece here, let me highlight it here. This lower piece here, this is the tribrac, and you can take this button here, turn it around, and take the upper part of the theodolite out. That was an interesting equipment. So it works, I wouldn't say the same way, but it's function to give you vertical readings from the vertical circle, horizontal readings from the horizontal circle. Let's see what we have. We have Thomas Jefferson theodolite. That's the theodolite that Thomas Jefferson used. You see, that's a very unique piece of antique here. I wouldn't say an equipment now, but that's an antique equipment here, made of brass and copper, belonged to President Jefferson, and made by Jesse Ramsden. Okay, so going quickly here, transit and theodolite operate the same principle. We've talked about that. Not, I would say no universally accepted difference, except the open versus, let me highlight it here, the open design versus the closed design for the transit and the theodolite. Theodolites are, of course, since they are, I wouldn't say more modern now, but they, at their time, they were more modern than transits, so that's why they had more precision and accuracy. Okay. Looking a little bit inside, you see the readings here, where we get the readings. Of course, now I'll give you a second here. I'll pause and you tell me, is this a theodolite or a transit? Some of you are saying transit, and that's the, or all of you are saying transit, and that's the correct answer. This is inside a theodolite. You see how the readings are reflected, and it needs, I wouldn't say experience, but it needs just some practice to know how to do the readings here. And once you know how to do the readings, you know the vertical from the horizontal, and it should be simple. Okay, so this is from the inside. This is how it operates from the inside. That's just the general scheme here. But let me get this picture here, or this sketch, and put it here. And now let's talk a little bit more about the theodolite than the transit here. This is the vertical circle. This is the horizontal circle. This is where you sight, so your eye or the observer will look from here. And then we have the eyepiece. This is the eyepiece. And then this is the object lens or the objective lens. This is the scheme of this instrument. Now, watch carefully here. We have the horizontal circle. And we have, this is the line of sight. So if I drew here, let me get a clear one so you know what I'm talking about. Clean this one. The easiest way is to put a newer one. Going just to make it a little wider here. It's okay. If I drew a line here, and this line is perpendicular to the horizontal circle. And I'm going to draw another line. Let's use a different color here. Through the lens here. So this line is going through these lenses here. This is what we call the line of sight. So if you got the lenses, let me draw them again. You have the object lens. This is the object lens. And then you have the eyepiece. And the line connecting the eyepiece, the center of the eyepiece and the object lens is what we call the line of sight, which is this line here, which is this line, connecting the center of the object lens with the eyepiece. If you want to see it in a different way, I can show it to you this way. Get this. Let me open a new paint. And going back to our paint, you see this is the scope here. There is a line connecting the center of the eyepiece with the center of the object lens. You see, this is what we call the line of sight. This is where you look through, and this is your eye here. And you look through, this is what we call the eyepiece. And this is what we call the object lens. So line connecting both of them. That's what we call the line of sight. This is the red line. And there is another line that I just highlighted, which is perpendicular to the horizontal circle. So if I go back here and let me cut the horizontal circle, bring it here. This is our horizontal circle here. There is another line perpendicular to the horizontal circle. It's this line here. Let me draw it in the same color. This green line, which I'm highlighting here as green. So hopefully we see these lines here. And then there is a third line, which is the line perpendicular to the vertical. Let me draw it in another color, which is this line here. That's the line perpendicular to the vertical axis. If I draw the vertical circle, sorry. If I draw the vertical circle here, this line here is what we call the this is the horizontal axis. Sorry, did I say this is the vertical? Let me write it down. Maybe I was saying them. So this is what we call the horizontal axis, and the green one, which is this one, maybe I said vertical, maybe I said horizontal. This is the vertical axis, and it's the same thing here. Maybe just because I was saying it quickly here. I'm more worried about the recording now. Okay, so this is the vertical axis. This is the vertical axis. Let me also write the line of sight. Line of sight. Okay, so these three here have what we call geometric relationship. We are going to talk about the geometric relationship between the horizontal axis, the vertical axis, and the line of sight. These three lines have to be perpendicular. So this is what we see here. We see the line. Let me come to this one here. Let me come to this diagram here. Okay, so the first thing is you see the vertical axis, which is in green. The vertical axis and the horizontal axis, and from the names they have to be perpendicular. You see the horizontal, I drew it in, it's going on with the colors here. Okay, so the vertical I drew it in green, horizontal in blue. So these two lines have to be perpendicular, the blue and the green. That's a very important concept. Due to a lot of things, the instrument could be defective, it's not calibrated, malfunction, all of these different things could cause these two lines not to be perpendicular and give you wrong readings. So that you have to calibrate your equipment every once in a while. Plus the blue and the green line, the blue and the green line, yes, they have to be perpendicular, as you see this perpendicular angle. The other thing also, the red, the line of sight, and the horizontal axis have to be perpendicular. So these two also have to be perpendicular, the red and the blue, which are the horizontal axis and the line of sight. So this line, the horizontal axis and the line of sight have to make a 90-degree angle. This angle has to be 90 degree. Not sure if you can see it here. Maybe let's take this and draw it here. This angle here has to be 90 degree. This is what we call, or this angle is the same. This has to be 90 degree. So these are two important geometric relationships that have to be satisfied between the different components of the equipment. Okay, so we are here. So that's the important geometric relationship. I'm going to write it here. I didn't want to write it in the presentation before I show it to you. So horizontal axis and vertical axis have to be perpendicular. I got this wrong. Okay. And then the next thing is, let me write it down, the horizontal axis and the line of sight have to also be perpendicular. So these two have to be perpendicular. Let me pause here just to make sure I'm doing things right, and then I'll come. Okay, so we were just talking about the different components of a theodolite, and just to highlight another advance in the theodolite equipment, that's what we call the electronic or the digital theodolite. So with the digital theodolite or the electronic one, now everything is done digitally. You get the readings on a display. The readings are done automatically. Actually, what happens here, and instead of using our protractors or the optical ones, now we use digital protractors here, or digital circles. And the kind of work, I mean, it's a little bit more electrical engineering here, but there is this rotating circle, and the rotating circle has these alternating white and black sectors. Light passes through, and then once you rotate it, there is a sensor here that can sense how many sectors you rotated. And then again, I'm simplifying things here a little bit, or simplifying them actually too much, but then the sensor here can determine how many sectors you passed and then convert this into a horizontal or a vertical angle. Couple of the old theodolites here, the T3, that's a very precise one. The DKM3, the current DMK3, that's also another precise one. In the old days, we used to observe stars. So we had what we call the broken telescope instrument to observe stars. That's one of them. That's another one. And the idea here about using the broken telescope is we are observing stars, and stars have very high altitude. So if you looked at paint, if you looked at the star here with our equipment, that's the tripod, and the star is going to be all the way somewhere here. And we have a star here. Yeah. So with that altitude, if this is the vertical axis here, and you are observing the star, let's pick another color here. This angle here is going to be too small because you are observing Polaris and such stars. So you might have difficulties observing these stars, and that's why they made the broken telescope here. That's why they had these broken telescopes. Okay, that's not really an important part, just wanted to show you. Now we go to the second. Okay, so the second part here of the equipment or of the total station, if you still remember, is the distance measurement unit, and that's done through an electromagnetic device or an EDM device. And the first EDM device was introduced by the Swedish physicist Mr. Bregstrand in the late 50s, and that's the early version of it, and that was called at that time the gidometer. Now the problem with this gidometer, you see here the front and the back of the gidometer, the problem with this device is it was using visible light, so we cannot really use it in daytime. We only had to use it in nighttime, otherwise it interfere with the sunlight. It was able to measure distances up to 40 kilometers. So the range of this equipment was about 40 kilometers, but again, the problem is not being able to use it at daytime. Then, about 9 years later, came what we call the teller meter here. And that was designed in South Africa by Dr. Wadley. And the good thing about this instrument, the teller meter, which is the one we see in these two images to the right bottom of the screen here, the good thing about it, it used microwave, and this is what I'm highlighting here. So with microwave, we can use it daytime, nighttime, plus also it had a longer range, which was 80 kilometers. And then you don't really need to know or to remember the ranges, but you need at least to know which one was using the visible light, which one was using the microwave. I'm going to show in the next few slides a couple of these instruments. This is an EDM. Now, with an EDM, as we will see here, it needs a sender or a transmitter unit and a receiving unit. So we'll take a look at these, but this is just one of the early models, or actually two of the early models here. These are a couple of these models, and you don't really, again, need to memorize the range and the accuracy, but I'm just going to grab this here and go to paint and highlight some of the properties of each of them. So let's see, paint will show up here. Paint is here. Okay. So this is the picture I had here. So in the early 60s, we had the MRB2 that had a range of 40 kilometers, but 1.5. If we zoomed in a little bit here, this is the one I'm talking about for those who are watching. And we'll highlight this. So the MRB2, that's the one here, and it had a range of 1.5 meters. The early ones that had good accuracy was the MRA30, and that had 15 millimeters. Again, you don't really need to memorize or recall these. And then in the 70s, we had the MRA5, that was about 10 millimeter. In the 80s, we had the MRA6, almost the same as the MR5. In the 90s, we didn't really have a lot of new ones. And then The other one that I would like to talk about is the MRD, which had about a decimeter. You know, 0.1 meter is 10 centimeters is 1 decimeter. So these are few of them. You don't really need to recall them or to memorize them. This is just some of them. Okay, so back to the presentation. These are some of them. How does it work? Here is the important part. Let me put this into the screen mode, sorry, the slide show mode, and then share the slide, show here. Okay, so hopefully this is working. These instruments work with what we call here the electromagnetic waves, And if you looked at the name here, an electromagnetic wave has both an electrical field and a magnetic field. The electrical field here is what we see in the orange, and the other one, which is the magnetic field, is the one we see here in purple. So each electromagnetic wave, when it propagates with these two perpendicular to each other, but it also propagates in a waveform. And the distance between two crests is what we call the wavelength. That's what I'm showing you here, which is what is shown here. And that's the distance between any two corresponding points. So even between the two throats here, it's still what we call the lambda here. That's the wavelength. That's a distance. That's measured in meters, centimeters, foot, whatever. And it also has another. It also has another property, which is what we call the frequency. So the frequency here, a very simple way to understand the frequency. Let's say you stand by this door here. So we have a door here that I'm highlighting with red. Maybe let me use another color here. A blue here. If I'm standing here and counting how many full waves are going to pass this point, that's the frequency. That's the frequency. So if you have, let's say, 10 of these cycles, full cycles passed in a second, that's the frequency. And the frequency is measured in hertz, not in mega. Well, we measure it in megahertz, but when we apply our equations, make sure you put it in hertz. Make sure to convert your units into hertz. And the wavelength, usually in meter or centimeter, depending on what you're using. And then the carrying energy is another property. We're not really interested in it in this class. Okay, so next slide here is going to show you the big spectrum of the electromagnetic waves. It starts from gamma ray all the way to radio waves, or you can say it flipped. It starts from the radio wave to the gamma rays here. And this is the wavelength of the gamma rays, 10 to the power of negative 12, with a frequency of 10 to the power 20. Radio waves have wavelengths of about 1 meter, and their frequency is about 10 to the power of 10. Our eyes are only capable of seeing this very small, tiny part of the electromagnetic wave, which is what we call the visible part of the light, which ranges from 380 nanometers to 780 nanometers, which is 3.8 times 10 to the power of negative 7 to 7.8 to the power 2 times 10 to the power of negative 7. So that's what our eyes see. So what does this has to do, what all of these things have to do with our class here, or with our part? Because all of the EDMs, or the electromagnetic distance measurement device, will operate in this range here. That's the range. Let me, let me end this and go and take this here, and then go to paint and no, doesn't work. Okay, don't save. So our EDMs, our electromagnetic distances, work in the, if you looked back here in the PowerPoint slide, let me grab this here for you guys, work in this range, 0.6 and 0.9 micrometers. So some work very close to the visible light here. They work in infrared and red lasers. So depending on the instrument, the company, the brand, they work in this range, the 0.6 to the 0.9 micrometer here, which is very close to our visible light here, somewhere in this range here. So most of them work in this. So remember, red laser, infrared. I'm not really very interested in the numbers, but at least knowing the red laser and the infrared. Okay, going back to the total stations here, or the EDM. When these waves propagate, I just mentioned that they will have an energy, and a very important characteristic of the energy is the velocity of this energy. How fast does this wave propagate in the air or the media that's going to carry it? That's a very important thing. And I'm going to take this screen, take it to the paint here to talk about it in a little bit in more detail. So new, don't save. So let's take a look here at this velocity thing. So getting back here, this is the equation we are using, and we were saying that this wave is going to propagate like this, and when it propagates, it's going to propagate with a speed. And this speed is really very important for us, whether it's propagating with the V or the C. So what's the difference here? If it's propagating in vacuum, which is this here, that's the speed of light. It's going to propagate with the speed of light, which is what we usually call the 3 times 10. Let me write it down. This C here is what we call 3 times 10 to the power of 8 meters per second. That's the speed that we recall from physics. That's in case it's propagating in vacuum. That's in case it's propagating in vacuum. Let me highlight this for you here. Now, of course, our waves are not going to propagate in vacuum. They are going to propagate, for example, for our EDMs, they are going to propagate in air. Some other electromagnetic waves, like sonar, will propagate in water or will be moving and transferring in water. Some other electromagnetic waves, like visible light, will propagate, for example, in air or glass. So when they propagate in different media here, what's going to happen is they are going to, when they propagate in these different media, they are going to be slowed down, because instead of propagating or moving in a free vacuum, they are going to be faced with the particles of that media here. So they are going to be slowed down. And that's why when they propagate in a media, this C here is going to be a little bit less. The C is going to be a little bit less. And that's what we call the V here, or that's what we refer to the V. And this V is going, we just said, to be less, and it's going to be the C divided by a number in the denominator here, which is a little bit bigger than 1. That's what we call N. That's the refractive index here. That's this part, the refractive index. And that refractive index is for sure going to be greater than 1. I'm going to type it or write it here. That's greater than 1. And you have some numbers here, 1.0001 to 1.005. Hopefully that makes sense now. Now, in any media here, when this wave is propagating in the media, let me draw it in a different color here, make sure I have the brush. So now when it's propagating with V here, that's, let's say, in air, this is V, and this is in air here. It could be 1.000, the n, I mean, 2, whatever. But the v is for sure going to be less than n. So the v is for sure going to be less than c. Just typing n. Why? Because we divide by, that's not a good c. That's a good c. Now, okay, so now we know that v is less than c. What's the next thing? Well, we also know from this equation here that I'm going to highlight that v equals lambda times f. So this v here, oops, equals lambda times f. So let's see an example here. How do we apply these equations to determine either lambda or f? Let's see the example I prepared for you here, which is this example. I'm going to take it. Okay. And put it in here. Don't save v. And need to move this here. And move back to Paint. And then what else do I need to do? New, don't save. So this is the, let me make sure I'm sharing the Paint here. Actually, I was not sharing Paint, so now you should see the example here. So let's read it together. The what actual wavelength, so we are looking for the wavelength. I usually would like to highlight the things here, whether what's given or what's required. So it's asking us for the wavelength resulting from transmitting an electromagnetic energy through an atmosphere having an index of refraction. So I'm giving you the index of refraction here. So n is given. If the frequency, and I'm going to work with A and let you guys work with B. So you're given the frequency, and you're also given the speed of light in vacuum. So if you think about it here, you know that V equals exactly lambda times F. At the same time, V equals exactly C divided by N. So what in these four are you given, or what in these five? You are for sure not given V, you are given F, you're not given lambda, so that's a question here, or a question mark. That's the required. You are given C and you are given N. So what can you do here to get lambda? Exactly, you just rearrange term. You say lambda equals C divided by N. I'm just going to make it in one line, and then add another denominator here to put the F. That's it. And then you plug the numbers. Let's plug the numbers here. Let's see if this thing is going to help us. So what's C? C is this value. Okay, Control copy, Control C. Perfect. And then you divide this, let me use the correct color here, by N. Actually, working with a computer is nice here. Instead of writing these numbers by hand, Paint is helping. Oops, I need to copy this. So, well, I can just say divided by, make this bigger, 1.004. That's 1006. That's the number given. And then you divide by what? And then you divide by, am I missing a zero? Yep. Let me type it again. 1.1236. Okay. See, I hear you guys saying there is a missing zero here. Okay. And then you divide by F. And this is F here. 29.988. That's it. Think about it. Am I missing anything? I hear some of you said, well, you just said you cannot use megahertz. You have to use hertz. So I have to convert megahertz to hertz. How can I do this? Well, I'll give you a second here. You know how to convert megahertz hertz to hertz, you multiply by 1,000,000. 3 zeros, then another 3 zeros. So that's how you do the conversion between hertz and megahertz. And then you do the math and you get the answer, and the answer is displayed for you here. It's 9.9908 meter. And you have another example here, so please work it out also and make sure you get these numbers correct. Okay, so let me proceed here. How does it work? I'm going to show you now. In very simple terms here, if you looked at how it works, this is the total station. We have to have a reflector here. So this young boy here is holding the reflector for us. It has to be leveled. The level is somewhere here, the hand level. We'll assume it's leveled. And then we turn on the total station and we let it emit the LiDAR. And then the LiDAR propagate as waves. It goes all the way until it hit the reflector. The reflector, as I'll show you here, is made of glass. So what will happen here is the glass is going to reflect or bounce back this wave here. And that's how the wave will go back, straight in line all the way until it hits the equipment. Now, to understand this in very simple terms, that's not really what I'm going to say. It's not really the actual math model. But this wave here, to just simplify things, did go hit the reflector and bounce back. So it took a time t here to do that. And if you multiply this time by the speed of light, if it's vacuum, some of you will say, well, it has to be the speed of light in this media. I agree with that. So for simplicity, let's assume that it's the 3 times 10 to the power of 8. That will give you this distance going and coming back. So this is the distance here. However, the distance that you just computed is twice the measured distance. So you have to divide this by 2. And this is the equation you see here. If you multiply the speed by the time, you get the distance. Okay. These are the reflectors. You see here, all the reflectors are made of these reflected parallel or the glasses themselves. And the purpose of using the reflector is to orient and bounce back the light or the laser beam here, or the electromagnetic wave. We have different styles of the reflectors. We have the triplet for long distances. We have the single ones. This is the tri-brack here. And it has to be leveled, or we can use the reflector on the prism rods. These are some of the early versions here. You see how many prisms we are using. This is for very long distances here. And this is the laser for these very long distances. This was during geodetic measurements here. Now, we do have what we call reflectorless total stations. And please be aware, reflectorless total stations are completely different than the other total stations, or the ones that I'm just going to show you here, which are the robotic ones. There is a big difference. Robotics could be reflectorless or no. Reflectorless could be robotic or no. So the ones we have in the lab that we are going to use in 134 are reflectorless. You can orient it toward any surface, like this gentleman here is orienting it toward this corner here without a reflector, and then the beam. But you have to, I mean, when you're doing this, you just have to make sure you are using the right mode for the EDM. And I can show students in my lab how to do that. But in any way, when you orient it in the prism-less mode or the reflector-less mode, it can reflect and bounce back from any surface, or most of the surfaces, of course. Some surfaces like glass or something, you have to be careful. Now, the very important thing that I would like to highlight here, make sure that the beam is not interrupted. So like for this case, you send the beam, it goes all the way, all the way, all the way, all the way, all the way here. But you are not really sure if it's going to bounce from this point or this point. Or part of it might bounce back from here, part of it might bounce back from here, give you false distances. So that's why these are very useful, very helpful, but you need to be careful which surface is it bouncing back from, or is it interrupted or no. So that's very important here. Other things, it also has to do something with the surface reflectance. You remember I said some surfaces and lighting conditions for sure. Some surfaces it will bounce back good. Some surfaces like glass, it could be, well, let me stop here, the train is coming. Okay, so I'm back here. Let's go to the screen. So just make sure the signal is not interrupted when it's bouncing back. And then there are also what we call the reflective survey targets. And these targets, you can set them here, glue them, and attach them or stick them to different surfaces. And the best example to use them is when you are monitoring, for example, if you are monitoring the formation of this dam here. So you set these targets, and then you have a fixed point here, and then you come every, let's say, month or 2 months or 3 months, depending on the application, depending on what exactly are you measuring, and then you measure if they have moved. If they have moved, that means there is a deformation. Or this here, this is a beam. We had 2 columns like this. You guys are engineers, and then there was a beam on top of these 2 columns, and then we put the survey targets here. We put these targets here. We measured them, we measured their positions, their X, Y, Z, and then we put loads vehicles here on the beam, so it's going to deflect. That's what's going to happen here. Let me use a different color. So what's going to happen here, this beam is going to deflect like this. Somehow, maybe I made it a little bit bigger, but that's how the beam is going to deflect. So the targets will move. Then you measure the movement of the targets here. And you can do this like every once a while, or depending on the application again. Or a retaining wall like this. Maybe you measure it before putting the rocks and then after putting the rocks and see if it's deforming. So that's a very good application for these targets. Now, nowadays with the reflectorless, which is this one, you don't really need these surveying targets, but if you need them for any purpose, if the surface does not really reflect the signal that good, then you can use them. This is an example of these reflector targets here. The good thing about the reflecting targets or the reflective surveying targets, it has this cross, so you can precisely, hopefully I can get the cross here, you can precisely determine the position that you are looking at. Nowadays we have the robotic. What is the robotic? The robotic is just the total station operated by one person here. That's the whole thing about the robotic. So he has a data collector that can talk to the equipment and can orient the equipment from far away. So that's really the thing, but still it can work with a prism or without a prism. It really depends, but that's the whole thing. So you have a keyboard or the data collector that can do that for you. Now, some of the sources of errors: personal errors, careless centering the instrument or the reflector. Make sure you center it correctly and plummet. Error in measuring the instrument and reflector height. When you use these equipment, you have to make sure that you measure the instrument and the reflector height and input them or enter them in the system. So you have to make sure you are doing this correctly. We talked about the velocity, the speed of light. This is affected by temperature and pressure. So usually we measure the temperature and the pressure and we input them. Mistakes in making readings and writing them down. If you are not using the memory cards make sure you double check your readings when you write them down. Now, some of the natural problems here, we talked about this wave. So what if this wave here in very long distances here, where it's going from the EDM to the reflector, what if it's interrupted somehow? Let me get the highlighter here. So it's going through different atmospheric conditions here. Temperature will vary, and that can affect your measurement. One of the problems also, if the line of sight is too close to the Earth, the beam or the light here, if it's too close to the Earth's surface, the laser here will have much more refraction and it will bend more. So if you remember, we said this is the instrument, and let's say we have the laser going in a straight line. If you are too close to the ground here, this light is going to, oops, it didn't bend with me. Well, let me draw it in, well, no, keep it, okay. Let me, okay, let's go to paint. And let me make sure I'm sharing the screen. I did record a lot of these videos and forgot to share the screens here. So I had to redo them. So this is the instrument. Am I sharing paint? Yep. This is the tripod, and then we have the instrument here. Like this, and then we have the light ray, and let's assume the light ray is straight line. If you are too, well, in all cases, it's not really going to be a straight line, it's going to bend a little bit. But if you are too close to the ground, it's going to bend much more here. Of course, the bend is not that big, but I'm just demonstrating it here, like with the mouse here. So that's a critical factor here. So going back here to my presentation, you have to be careful with that. Okay, some of the applications that you can use the instrument in: topographic surveys, where you measure the shape of the Earth, you create maps, contour maps, you map buildings, ground, all of this. Hydrographic surveys, when you map oceans, when you map lakes, when you map shorelines. Cadastral survey, when you are doing boundary surveys. Construction guys, we use the total stations a lot, so construction projects. When you are doing route surveys like rail and roads. Mining surveys, when you are doing surveys under the earth. So all of these are different applications here. And of course, you are using the total station in your 134 labs to do the traverse and then to do the mapping. So just to highlight that. Now, the very basic and important, let me hide this from you guys. That's just a triplet here, using it for this class. Okay, the very important thing that I would like to highlight, that the signal here, the EDM or the total station, is measuring the slope distance, because the signal is going through this line here. The signal is going through the slope line. So what's being measured is the slope line. And I need you to be very careful with this. It's not measuring the horizontal or the vertical distance. It's measuring this wide or this red line here. Then you can use the angles that it measured. You can use the vertical angle that it measured. Let me highlight this here. You can use the vertical angle between the signal and the horizontal plane to compute horizontal and vertical changes. So let me show you some of this here. some of the things you can measure. With this here, we can measure the horizontal angle. So I'm setting the equipment at point I, first looking at point J, and on the horizontal circle, I read the 240, 40, the number I'm highlighting here. Let's make it 24 so you guys can see it. And bold it, it's actually bold. And then you turn the equipment. Remember we said we turned clockwise. You turn clockwise. You turn clockwise until you hit the other point, point K. And then you measure the angle and you get another number. What's the horizontal angle here? It's the difference between these two readings. And that's what I'm showing you guys here. You see, you got 240 at the first one, you got 280 minutes and seconds, and the difference is the 40-15 here. 242 minus 41, 1 second. 55 minus 40 is the 15 seconds, and 280 minus the 240 gives you the 40 seconds. So that's our horizontal angle. We can measure distances. Usually when we measure distances between, let's say, point I and J, you have to measure, you don't have to, but it's preferred and recommended that you measure it from both ends and then take the average. That's what you are going to do in your labs. So that's how you can take distances. You can also measure vertical angles. Now, be careful when we talk about vertical angles, because the instrument, when it's set up, let me get the instrument here. Let's get this print screen and go to Paint, because that's an important concept here. And let's share Paint. This is, you don't need the here. Control new save. Okay. When we measure vertical angles, please be careful with this here. If we put the vertical circle, this is our vertical circle. I'm just going to move it here. This is where we read the readings, so it gets clear here. Where is the 0 here? Where is the 0 here? Well, the 0 here is all the way looking to the top here. So if I have, this is where the 0 is going to look to. This is our 0 here. This is where the 0 is. Let me write it down. This is 0. And then on the vertical, but opposite to the 0, so here you see 180. So this is the 180 of the equipment. That's important here. What does this mean? Why did I do all of this? Well, I'm showing you all of this so that you know when you are looking exactly horizontal, when the telescope here is looking horizontal. Can anyone guess what the reading will be if I'm looking this way? This is my scope here. This is the objective lens, and this is the eyepiece. That's a nice scope here. What is the reading when it's horizontal? Exactly, it's going to be 90 on this side, or if you are looking backward, it's going to be in this side to 70. So when you look here and you see the 90, that means you are looking horizontal. What do I want to tell you also? I want to tell you if you are looking downward, like if you are looking in this direction, what do you expect the reading will be? Exactly, it's going to be a little bit above 90 if you are close to the horizontal surface. So it's going to be between 90 and 180. And if you are looking here, the reading is going to be between 0 and 90. So where is your angles here? This is the angle that the instrument is measuring. That's what we call the zenith angle. But your vertical angle is this angle here. And I'm not going really to put it with an arrow, but just let you know, if you are here, it's going to be positive. If you are here, it's going to be negative. So this is here what we call the zenith, angle. And the zenith angle here is what ranges from 0 to 90. So if the zenith, which is the reading this plate to you, is 90, that means you are having a vertical angle of Exactly, 0. How many times can you see a zenith angle of 0? You never can see that because then your scope is looking upward. Hopefully that makes sense. So if zenith here, for example, is 85 degrees, that means your vertical angle is positive 5. If it's 90 degrees, then your vertical angle exactly is 0. If it's 95 degrees, then your vertical angle is -5. You're looking downward. So please be careful when you do the math here. Okay, back to the PowerPoint. So this is an example here just to show you how it works. And then if you would like to have a look at this, so this is your 90 minus, this is the zenith here, this is your vertical angle. I'm highlighting here the vertical angle, making it in a bigger font here, 24, that's this angle. And then here it's going to be, you see the negative here, you see the negative sign. Let me just move this so I can make it bigger and make this in a different color. So this is here -22. So what I would like to show you here is one of the examples we can use the total station in, and I'm going to leave the trig here for you guys. You guys are much better than me in doing the trig here. Just to let you know that an example like this, if I would like to get the, for example, the height of a flagpole, I can get the angle to the top, the angle to the bottom, and if I have the distance here, let's assume I'm using a theodolite, not an EDM, I can measure the distance with the tape and then get both heights, add them together. I didn't really describe this too much on purpose, just because I want you guys to do the math here. That's a very simple example. Again, I have a theodolite. I don't have an EDM. I don't have a total station. With a theodolite, I can't measure distances. So what I did here, I measured the distance with a tape. And then I measured the vertical angles to the top and to the bottom. And then from these two vertical angles with the measured horizontal distance, that's measured with a tape again, I can compute the height of the flagpole or a building. So make sure you know how to do that. Another example, let's say that I would like to get, again, with theodolites, I would like to get the difference in elevation between point K and point I. With the total station, if you input the height of the instrument and the height of the reflector correctly, it will compute the difference V here. But I would like you to know how to do that with the math here. So with the math, or with the theodolite, let's assume you have the theodolite here and you have the top here. So what you can do here is you can do the same thing. You can measure the horizontal distance, copying this and just pasting it here. And then you measure the slope or the vertical angle, and then you compute S. How can you compute S? I'll let you guys think about it. I know these are simple trigs here, so that's why I'm not really focusing on it a lot. Any idea how to compute S from H if I measured? So S equals, I measure the horizontal distance. I would like to get S. S equals what with respect to H? Leave that here. Then you get the slope distance here, and then you can just find the difference V. That's the difference V between this point and this point. Very simple trick. S times sine theta, and since theta is looking upward, it's going to be positive. And then you add HI, you subtract HR. So a good way to show you this, I'm going to take this arrow here, put it here, and then, so what I'll do here is I'll put this arrow here and then show you on this side a simple way of doing it to understand the math. So this is V here. That's what you're looking for. and this is HR here. So you can see both these, the V and the HR. On the other side, this equals to HI plus this thing, which is S times sine theta. That's how you can get this equation from, or this is where you get this equation from. So you add these two, they equal these two. And then you can say that V equals the S sine theta plus the HI and minus HR if you send HR the other side. Let me grab it and put it in Paint so you can see it clearly. And sure, this is Paint, so hopefully Paint. Okay. This is what you see here. HI plus sine theta gives you all this here, from the top all the way to the bottom here, this whole thing. HR plus V gives you the other side. So if you rearrange the terms, you get our equation here. Okay, going back. So please try to sketch it and make sure you understand what's going on here. Couple of the applications, other applications, you can use the total station to stake out, to set stakes, to set building corners, to set centers of roads, for example. You can use it to measure areas or to compute areas actually. So you set the prism pole on different points and then have the total station observe these points and then compute the area for you. You can determine remote height. If you would like to get the depth, for example, in this case here, you can't really measure all the way the depth or the height of this, the height of the bottom of this bridge. So you can bring the prism pole all the way below the bottom of the bridge and then shoot it and then shoot the vertical angle to the point above it and have the instrument compute this distance for it, to compute the distance or the depth or the height from the ground to the bottom of the bridge. You can have it compute volume, stake out grids, stake out curves, lots of applications. That makes this class, again, just to make sure, this is the February 13th class. Thank you and goodbye.